Hello, and welcome to the second PowerPoint presentation on Energy Science Fundamentals. In this presentation, we cover the various forms of energy conversion efficiencies, and the laws of thermodynamics. So let's go ahead and get started. So again, this quote taken from the Energy Reader suggests that a basic understanding of energy fundamentals is a critical part to energy literacy. And here in this presentation, we continue that process by looking at some key energy science concepts. So the first concept is the idea that there are a variety of different forms of energy. And this chart here on the right divides them first into potential energy and kinetic energy. And then under each of those different categories, there are a variety of additional forms of energy. Chemical energy, the energy within the bonds of materials, largely fossil fuels, coal, oil, and natural gas, food for that matter, are also chemical forms of energy. On the other side, kinetic forms, this is kind of energy in motion. We've got energy, what they call radiant energy, which is waves of energy moving through space. Thermal energy, that's the vibration of the molecules of a substance, represents an important form of energy. And of course, there are others, including electrical energy, which is the movement of electrons moving through a substance. So essentially, our energy economy, the devices that we rely upon on a daily basis, take one form of energy and then convert it to another form of energy. And here is a simple example. We have coal, which is a chemical form of energy, and that is burnt in a coal-fired power plant. So we're converting that chemical energy into thermal energy, and that thermal energy in a power plant is used to create mechanical energy, motion, so that we can spin a generator where you've got copper wires spinning around a permanent magnet, which creates a current and a flow of electrical energy. Chemical to thermal to mechanical to electrical energy, which then powers the light bulb in your home. So by and large, most of the energy devices that we use, the original process is a conversion from chemical to thermal energy. And so as I just described, a power plant, most of the power plants that we rely upon in this country burn fossil fuels, coal, natural gas, or not so much oil, but primarily coal and natural gas. Well over 50% of our electrical energy is produced using these fossil fuel resources. And it's a chemical energy process. The chemical energy bonds within coal, within natural gas, are burnt through the combustion process, creating thermal energy, which again is translated into mechanical energy and then electrical energy. But the core process of a vast majority of our power plants is chemical to thermal energy as the starting point. And then there are other conversions that we experience on a daily basis. Here we are entering the heating season here in Vermont, and we'll soon be burning chemical energy in the form of wood and wood stoves, or oil or propane in a furnace. And that's the direct conversion of a chemical form of energy to a thermal form of energy, which allows us to stay warm during the cold winter months. In the center, we see someone cooking on a grill. And again, we typically will use fuel, a chemical form of energy. Charcoal is a chemical form of energy, and we ignite it and we create thermal energy for cooking. Many of us cook on stoves that use propane or natural gas, conversion from chemical energy to thermal energy. On the lower right, we have an example of a vehicle. The starting point of a vehicle, ultimately we want to create motion, kinetic movement of the vehicle, but the starting point is this conversion of the chemical energy in petroleum and gasoline, converted to heat, and an engine, internal combustion engine, is a heat engine which converts that thermal energy into kinetic energy or motion, which then drives the vehicle. And on the bottom left there we have food, which is a form of chemical energy. We consume food, and that food is processed in our bodies, and much of that chemical energy is converted into heat to maintain our metabolisms. And there's other forms of energy that are being processes in our body that are using that original chemical energy found within the food that we consume. So here are several other types of energy conversions processes, devices that we rely upon. They're less common. Starting on the bottom, we have a nuclear energy. There is, although it's I would not say it's actually quite common. It's used primarily for electrical generation. I think 18 to 20% of electrical energy is produced using nuclear energy. So nuclear energy is the bond within the nucleus of atoms, and we split that bond, and it generates a tremendous amount of thermal energy. And that thermal energy again is used to create steam and run a turbine, which generates electrical energy. And then here we have in the middle on the bottom, we have an example of a dam which uses gravitational energy or potential energy, the position of water above a dam, and you release that water, that potential energy, which is being driven by gravitation, and it will drop that water. We can convert that kinetic energy, that motion of the water, using a water turbine to spin a shaft, which spins electrical wires around, copper wires around a permanent magnet, again to generate electrical energy. So on the top left there we have wind turbines, and wind turbines are the direct conversion of kinetic energy, the movement of air, into mechanical energy and then electrical energy. We use the wind to push the blades, turning the shaft, and that shaft allows us to turn copper wires around permanent magnets to generate electrical energy. On the upper right we have a photovoltaic panel. Photovoltaic technology takes radiant energy from the sun, and converts it directly into electrical energy. And we are seeing more and more of those technologies being deployed within the United States and globally as well. And on the bottom right we have an example of ocean energy. There's a couple different ways to use ocean energy. One is using motion of waves to run a generator. Again, it's converting kinetic energy, the motion of the waves, turning a shaft so that you can generate electrical energy. And then also a different, very much in its infancy stage, is what we call tidal energy. That's another form of ocean energy, and that requires the movement of tides in and out to allow various devices that can capture that motion and convert that into electrical energy. And that tidal energy is really gravitational energy. That's the position of the moon that drives the tides in and out on a daily basis. So these are, again, other types of energy conversion processes, but by and large, most of our energy economy rests on this conversion of chemical energy into thermal energy. So we want to understand what the conversion efficiency is from these different processes. So this equation, it's a ratio. You've got the useful energy out divided by the potential energy that's put into the system. It gives us what we call the conversion efficiency. So for example, a coal-fired power plant again converts the chemical energy of coal into thermal energy and then mechanical energy, but ultimately we want to know what the conversion efficiency is from that original potential energy in the coal to the electrical energy. And a coal-fired power plant typically would be about 40% conversion efficiency. So 40% of the original potential energy in the coal is converted into electrical energy. Another example, as we mentioned just a moment ago, is photovoltaic technology. And photovoltaic technology converts solar radiant energy directly into electrical energy. So the potential energy striking a solar array, the percentage of that that's converted into electrical energy is roughly 18%. It varies depending on the type of photovoltaic technology that you're using. Anywhere from 11%, and the highest photovoltaic modules achieve conversion efficiencies of 20-21%. And then finally, on the left, we have a vehicle. And a vehicle uses gasoline, chemical energy to create kinetic energy, or motion of the vehicle. And vehicles are approximately, the conversion efficiency of a vehicle is about 15%. So 15% of the original chemical energy in the gasoline actually is translated into motion, or kinetic movement of the vehicle. The rest of the energy is dissipated as heat. And with that will lead us to a discussion of the laws of thermodynamics. So all of these conversion processes and these conversion efficiencies are really bound by these basic laws of thermodynamics. And the first law is the law of conservation, which states that total amount of energy in the universe is constant. So again, going back to that example of the vehicle, we have this chemical energy in the gasoline, combusted in the internal combustion engine, driving pistons, and then ultimately driving the wheels. So although the conversion efficiency from chemical energy to motion is 15%, the other 85% of that energy isn't lost. It's just simply converted to different forms. Primarily thermal energy, which is released from the vehicle. And then you've got vibration, you've got noise. If you were to add up all those different forms of energy, then there would be an equivalence. The potential energy in the gasoline would be equal to all those various forms of energy which occur from the conversion process. But however, again, the conversion efficiency is the useful energy out as a percentage of the total potential energy of the input energy. So energy isn't destroyed or created, it's just converted from one form to another. And that conversion efficiency is really looking at the devices that we use on a daily basis. Again, the useful energy that we receive as a percentage of the total potential energy of the original source of energy. And the second law of thermodynamics is that disorder in the universe is always increasing. It's also known as entropy. The universe is moving from order to disorder. And how does this relate to energy? So if you think about a clump of coal, it's a very organized, energy-dense material. And so through the combustion process, we release that chemical energy as heat, and we can use it again to generate electrical energy in a thermal plant. But once that form of energy has been, that condensed form of energy has been utilized in this process, although the energy in the universe does not disappear, it's just in a different form. And once that order to disorder has happened, you can never recapture that energy and recreate it in that very energy dense form in this case, a lump of coal. So these two laws are very important. They really dictate the ways that we use energy in the machines and the devices that we use to convert energy. And it really has very important implications in terms of our current energy systems and where we might be going in the future. Okay, with that very quick introduction, thank you very much, and we will be in touch.